Wow, he actually explained quite a lot about the project in a few sentences. As he said, I am an architect, and I want to talk to you about Minibuilders, who we are, what we are, and also why we are here. So, in architecture, we have a huge link between what we can build and the technology. So, when steel frame came in, it meant architects could build taller, faster, better, and they could realize kind of all the dreams they'd had for all these generations of building these incredible buildings. But there hasn't really been many leaps in technology in the construction industry for a long time now. We're also a really messy industry. We produce a huge amount of carbon dioxide, and we're quite slow. We're quite slow at taking on a lot of the technology from other industries. We're kind of lagging behind what's going on in the aerospace industry and the car industry. We produce a lot of waste, and we waste a lot of time as well. I mean, you can be on site and the contractor will say to you, you'll say, when do you think it will be done? And he'll say, well, maybe 2 days, 3 days, maybe 3 weeks. You're not quite sure, to be honest. And as an architect myself, I know that on the computer I can design fantastic things. I can optimize structures, I can design all these great things, but there's kind of a massive gap between what I can design and what I can actually build. And this was kind of the catalyst for our project. So you design this fantastic structure, and then you transfer it to the site. So you build something to 0.01 millimeters of tolerance, and then you transfer it to the site where whole guys come, and they put scaffolding up, and they more or less build what you designed. So we started to look at how additive manufacturing can impact on the architectural scale. So you have fantastic 3D printers like we have at the back with Ultimaker, but they have the same problem. The object they produce is always smaller than the machine that is producing it. And this is a great technology. I mean, we can 3D print rocket engines that go into space. This is a fantastic technology that we want to harness for the construction industry, but we don't have the tools to make it work. They're not scalable. We have problems. So the Chinese want to 3D print buildings. So they built a 3D printer as big as a building. I'm sorry about the quality. It's all I could find on them. And it's massive, and it's just a bit silly, really. It doesn't work. It's not scalable. If you wanted to build the Empire State Building, you would need a 3D printer the size of the Empire State Building. There are also, I think a lot of you have maybe seen the houses that they're building in China with a 3D printer. And it's great, but it's built off-site. It's built in a factory. It's then brought to site, so then you have all the problems that you're putting this on a lorry and taking this to the site. And also, they're not buildings I think you would want to live in. They're not particularly nice. They're not taking any of the advantages we have of 3D printing. They're not optimizing structure. They're not doing all these things. So this was really the catalyst for what we wanted to do. So what we came up with is, instead of one large 3D printer, we created a family of smaller robots doing unique tasks that come together to build objects much larger than themselves. So this gets around a lot of the problems of scale and scaling up this technology. So the first robot is the foundation robot. Let's show you in action quickly. So this was when we were doing the 1-to-1 scale prototype in Barcelona earlier this year. So the foundation robot comes, it goes onto the base where we wanted to build our prototype, and then it lays the first foundation for the building. Just forward that on. I cannot. This then lays the path for the second robot. So then the second robot grips onto the layers already printed by the first robot, and then, as you can see here, and then travels around the layers previously printed, moving up into space. So then that leads to the third robot, which is the vacuum robot, because you have the problem with 3D printing of the layers. So you're always going to have the problem that you have a weakness in one direction. So the third robot allows us to move in kind of another dimension, moving across the minimal shell that we built with the second robot, depositing material where it needs to be deposited. But not only where, also into the lines of stress. So instead of just randomly putting the material, we can optimize the direction of the material, and this is very important. We also built our own software. I want to emphasize that we're architects, not software designers. So we built our own software to take all the data we had from other widely available programs and put it into these robots. So we built this software to be used on site. This was kind of idiot-proof software that we could use to test these robots outside. So this culminated in a one-to-one scale prototype earlier this year. And we learned a lot doing this because we were doing it not in a laboratory, not in a house, in a tent. We were doing this outside. We had huge amounts of problems, which I'll get onto in a second. So we built it next to water, and all our tests weren't next to water, so we had a lot more humidity than we imagined. We had sun, darkness. We had to change things on site constantly, so the sun was heating up the wood of the base, which was then confusing some of the sensors on the robot. So it seemed stupid. We covered it in cardboard, and it started to work. So we learned a huge amount just doing this on site, out of the laboratory. We have a lot to thank for that this is all open source. We opened all of this up, and it was a lot due to the maker movement and like the Arduinos that we all managed to quite easily learn how to program and achieve what we wanted to achieve. Because we're architects, we knew what we wanted to achieve, but we weren't roboticists or programmers, so we had to learn how to achieve our goals. Everyone always asks about the material, but actually this isn't the focus of this project. The material was an artificial stone, essentially, but it really isn't the focus of this project. The focus of the project is a new type of delivery system which is suited to the construction site. So we very quickly developed a material which we knew could do all the things we wanted to do, that could do double curvatures. But we still didn't quite reach where we wanted to go. We really want this material to be optimized, somewhat like a bone structure. We want it to be optimized in direction, in form, and eventually you get to some of the stuff that Arup has been playing with on a very small scale. So this is a node point for a building where all the cables come to. And because it's been 3D printed, it's 15% lighter because of the form that you're able to achieve. So if you're 15% lighter, it means you're using 15% less material. You're using 15% less CO2, 15% of the material being taken to site. You have all these advantages. And if you look at the shard or something like this 15% of the shard is a lot. So then this moves forward to what we're going to be doing over the next year. The next generation of robots are going to be a lot more exciting. They're going to be a lot more agile. They're going to be a lot smarter. They're going to have a lot more sensors inbuilt to them. They're going to be able to move a lot more freely around the building site. So then when we have all that data, we want to input this into a new piece of software that's going to allow people, if you imagine like a heart surgeon now can maybe do an operation in England where the expert is in Australia, you now have the opportunity that an expert in Australia can now oversee a building site in the UK. I don't think this is going to be, we're not going to be 3D printing buildings overnight. It's not going to be the whole building, but it's a step forward in this direction. So you're going to be able to check up on your robots on your smartphone. You're going to have access to all of this data that's being produced. So that's the end, but I would like to thank all the members of the team also, which is myself, Dori Sadan, Jin Shahui, Better Novikov, Christina Nan, and Sasha Jokic for all their hard work together. Thank you very much.